Welcome to our 3 p.m. press conference on opportunities latest from the Martian crater rim. We'll have 3 speakers in this order. Bruce Banerdt, project scientist for NASA Mars Exploration Rovers at NASA's Jet Propulsion Laboratory in Pasadena. Ray Arvidson, deputy principal investigator for NASA Mars Exploration Rovers at Washington University in St. Louis. And Stephen Squyres, principal investigator for NASA Mars Exploration Rovers at Cornell University in Ithaca.
Okay, can I have the first slide here? Okay, so Opportunity's been a very busy little rover, and I'm putting this picture up here just to sort of give some historical context. We started out up here at Eagle Crater quite a while ago, and we've been crater hopping south ever since, going to larger and larger holes in the ground. These are holes that have been excavated for our convenience by meteorites and asteroids, allowing us to get to deeper and deeper rocks, which sort of allow us to peer farther and farther back in the geological history of Mars. And so you can see we've been going south. The next slide gives sort of a timeline of going from Eagle down to Endeavour. And you can see there's 2 things that really jumped out at me when I put this together. And the first thing is this number right here. I mean, 8 years on the surface of Mars. I mean, that's just amazing. And furthermore, if you really look at the way these yearly tick marks line up, you can see that at about 5 years, you know, Opportunity really kind of cranked up its game, and it more than doubled its distance in the next 3 years, going from this point down to Endeavour. And so this is far from being a rickety old rover. I mean, she's really, you know, turned up the boost and gotten down there. And so we finally arrived at the rim of this crater. Next slide, you can see. That's about 4 months ago. We hit the southern tip of this feature that's what we call Cape York, and for the last 4 months we've been exploring along this ridge, and Steve and Ray are going to tell you about some of the discoveries that we've made here. Next slide, just to give it a little bit more context, we've gathered together the data from all the vehicles that have been sent to other planetary bodies besides the Earth. These are all the wheeled vehicles that we know about. On this plot we have the Apollo 15, 16, and 17 lunar rovers that were driven by astronauts, along with the Soviet Lunokhod 1 and 2, which were robotic lunar rovers, and then Sojourner, Spirit, and Opportunity on Mars. And you can see that Opportunity is solidly in 3rd place in the race for the long-distance trophy, and it probably has the best chance of actually doing better, as it's really the only horse that's still competing in this particular derby. So we're looking forward to surpassing the last 2. It goes to about 37 kilometers, so we're a little less than 3 kilometers behind right now. Okay, so as for Opportunity status right now, as of its last checkup, which was this morning, she's in excellent health. Really hasn't changed very much in the last year. It's been pretty stable. We've worn out a couple of pieces on it. One of the 4 steering motors is not operable. We've got an arthritic shoulder joint that limits the movement of the robotic arm, but doesn't really limit where we can put it, because we can sort of twist the vehicle around to make up for that. The mini-test instrument is worn out and is no longer giving us data on the infrared spectrum, and the Mossbauer spectrometer has gotten kind of weak and feeble as its radioactive cobalt source decays down to lower and lower levels, but it's still operational. So we have a rover which still has virtually most of the capabilities that it had when it landed, and we're still using it to do what it was designed to do, which is to be a field geologist on Mars. So for the future, right now we're coming up on Martian winter, and for the first time we're going to actually make sure that Opportunity is parked on a north-facing slope so we can get a little bit more solar energy on our panels. It's a little bit dustier than they have been in previous years. But this is, you have to realize this is a very different situation than you may remember Spirit was experiencing the last several winters on Mars. And in those cases, Spirit needed to get its panels tipped to the north in order to survive. We're not really talking about surviving here. We're talking about getting enough energy on the panels so that we can have an active scientific campaign all winter long. And so we're scouting out a few locations at the north end of Cape York, which have reasonably extended areas that all have slopes greater than about 10 or 15 degrees. And that should allow us to keep active scientifically all winter long, do analyses on various different bedrock targets that we might decide to look at more closely, and maybe even do some radio science tracking the Martian spin axis to tell us about the deep interior of Mars. So with that, I'd like to turn it over to Ray to talk about some of the scientific context of what we've been doing lately.
Thanks, Bruce. What I'll do is kind of set the geomorphic and geologic context on a regional to a local set of scales, and tell you a little bit about the mineralogy we infer from orbit, and then Steve will talk about the details of the measurements we've made since crossing over to Cape York and provide the punchlines. So luckily we're in a program of exploration of Mars, and we have Mars Reconnaissance Orbiter looking down at our site among other sites. And we'll talk about HiRISE data and CRISM data. HiRISE is the high-fidelity imager, and you can do stereo, and you can make topographic maps, and then you can make these kinds of perspective maps as shown, in which we've taken the topography from HiRISE stereo and just laying over that topographic model as perspective view with one of the HiRISE images. So we're looking from the center of Endeavour, which is 20,000 meters across, toward the northwest. What's important here? For 7.5 years, we drove over these sedimentary rocks, these sulfite-rich sandstones that we think formed in a combination of water and wind environment, largely arid but sometimes quite moist, and have done a suite of measurements. But in August, we crossed over to Cape York. And Cape York is one of the rim segments of Endeavour. This is an ancient crater that's largely buried by the sedimentary rocks. It's left over from late heavy bombardment, largely eroded down, but a different geologic terrain, as we'll see as we kind of go through my presentation and Steve's presentation. We have some information about the mineralogy from orbit, from CRISM, which is an imager but also a spectrometer. And back a couple years ago, there was a paper by James Ray and Geophysical Research Letters in which this area called Cape Tribulation, 80 meters tall above the surrounding plains, showed really good spectral evidence for a clay mineral called a smectite, an iron-magnesium smectite. We couldn't get there. We needed to get to the closest landfall from where we were in Victoria, and that's Cape York. Same geology, same kinds of rocks, we thought, based on the orbital characteristics, but we couldn't see large exposures spectrally of these smectites, but the geology was the same. So we wanted to get onto those rocks and make measurements. And we did. We came in from the northwest, and we entered the area around Odyssey Crater to make the first measurements. Interestingly, Botany Bay is kind of a wind gap between the various rim segments, and it has what's called a high thermal inertia from another orbital data set from Themis. High thermal inertia means that it has a fair abundance of rocky material exposed, and that's important in the story that I'll kind of weave as we go through the slides. So the next slide gets us a little closer. HiRISE is the same data, just more detail, and you can see Botany Bay and some other features. By the way, these features, Cape York, Solander Point, Cape Tribulation, are named after areas on the eastern side of Australia discovered by Cook when he was in the Endeavour exploring the Pacific. So we crossed over at Spirit Point, and you can see where the vehicle is today. We're up at the north because those are where the north slopes are, and we need to be at about 16 degrees to have a good winter campaign, 16 degrees to the north, and that's exactly what we're at as we speak. Shoemaker Ridge, an important part of Cape York to us. Eugene Shoemaker was one of the founding fathers of planetary geology, and he died a number of years ago. And we wanted to name a key feature of ancient rock, and we'll see, as we'll see, it's an impact breccia that's probably holding up Cape York. So the spine is called Shoemaker Ridge. And as Steve will say, we're going to make a Shoemaker formation and announce it in a few minutes. So we crossed over this bench, this area that surrounds Cape York, and then made measurements at the area around Odyssey, and then popped to the north to get to a good place for the winter site. And again, that high thermal inertia area turns out to be important. What's in the lower right are some CRISM data shown as false color, but we've done oversampling in the long track direction, so you get much better resolution than you typically do. This is a hyperspectral imager, so you can also pull out information that relates to the mineralogy, as we'll see on the next slide. Well, not yet. Okay. So this is Cape York, and this is unusual. This is still on the sedimentary rocks, these sulfate-rich sandstones, and you can see Odyssey, the crater off to the side, and a set of ejecta blocks on Cape York. This is the area that you'll see in a minute has a pretty distinctive signature spectrally that kind of fits into our overall story and the punchlines for today. Next slide. And that's a PanCam false color view when we are on Cape York, looking at the southern side of Shoemaker Ridge. And what you see is spectral evidence from PanCam and from the other observations we made. Cape York is basically a basaltic material, basaltic sand, some rock clasts, and some outcrops. Next slide. Now we get to the spectra. This doesn't look like much, folks, but this took me about a month and a half to do. So I hope you'll appreciate it. And that we're looking at the brightness of the surface on the y-axis versus wavelength from the visible to about 2.5 micrometers. The black line is a model that shows you basically what CRISM sees with all the gas bands. Those dips are due to carbon dioxide. There's carbon monoxide, there's water vapor, there's dust in the atmosphere, there are ice aerosols in the atmosphere. So when you remove all that and you look at the surface spectrum, we're looking at the southern part of Cape York and the northern part of Cape York. And if you talk to me afterward, I'll explain how we can actually say this is basically dominated by pretty dry basalt. Pyroxene is the dominant mineral we're seeing, mixed with nanophase iron oxide. That's what we're seeing dominantly in Cape York. Next slide, though. If you look at the highest thermal inertia parts of Botany Bay, and you do some ratio, and you take the spectrum for the highest thermal inertia parts divided by the average, what you get is a beautiful spectrum for the mineral gypsum, which is calcium sulfate with 2 waters. This is the first evidence for aerially extensive gypsum as bedrock. And it's important that it's right in contact with this ancient Noachian crust, as Steve will explain when he goes through the information that we've gotten from the surface. Next. And then finally, here's a super resolution PanCam view taken from our current site, which is probably the winter site, kind of looking back. We couldn't go to the inboard side of Cape York, the southeastern side, because we didn't have the right tilts. The energy wouldn't permit. So after we're done wintering over, we'll hightail it to the inboard site, because geologically, and there's some spectral evidence from CRISM, that's where the clay minerals are. And then we eventually want to get to Cape Tribulation. Are we out of warranty with this vehicle? You betcha. You know, it's going on 8 years, but we're not done yet, so there's still a lot to do. But we have a nice self-consistent model with what we're seeing from orbit now and what we're seeing from the surface. And then Steve will provide the details of the surface measurements that we've done.
All right, thanks, Ray. It's really nice to be back here at AGU doing another press briefing after almost 8 years on Mars. To me, the coolest thing about what's going on with Opportunity right now is as soon as we got to Cape York, it just felt like the mission started all over again. It was like a new landing site. We moved into fundamentally different geologic terrains, stuff that we had never seen before. And so it really, really feels like a new mission. If we could go to my first slide. What this does is it shows you again the path that we have taken since arrival down here at Spirit Point back in August. Drive by of little Odyssey crater there, and then up and along the crest of Shoemaker Ridge, which forms the spine of Cape York, back down to catch some really important science right here, and then this is where we are today. Next one. Okay, so as Ray said, we have named the ridge that forms the spine of Cape York Shoemaker Ridge, after Gene Shoemaker, and it is the type locality for what we are calling the Shoemaker Formation. These rocks that comprise the Shoemaker Formation are very ancient. impact-produced rocks along the rim of Endeavour Crater. And this is one of our first really good examples of rocks from the Shoemaker Formation. This is a rock called Chester Lake. The scene that you're seeing here is roughly 50 centimeters or so across. And this is very typical of the rocks that we are seeing all along Shoemaker Ridge. This is at the south end of Shoemaker Ridge, but we're currently way up at the north end, and the rocks there look exactly the same. They look exactly the same texturally, and they look exactly the same in terms of their composition. Now, the composition of this rock is actually quite similar to the composition of some rocks that we saw over at the other landing site, at the Gusev Crater landing site with Spirit, completely around the other side of the planet. This stuff, as Ray mentioned, is basaltic in its composition. It has some subtle differences from what we've seen before in terms of its composition, but it's fundamentally a pretty familiar looking rock in terms of its chemistry. Its texture, however, is different from anything that we've seen before. And the texture of this rock is what a geologist would refer to as a Squyresite breccia. That's S-U-E-V-I-T-E. And Squyresite breccia is well known from impact deposits on Earth. You can see what you have as angular chunks of rock that are embedded in a fine-grained matrix. The fine-grained matrix was probably partially molten by the enormous energy of the impact at the time this was emplaced. But this is just a classic visual example of what impact breccias on Earth often look like. Next one. Now, this is an interesting one, and this one poses some kind of puzzles for us that we're still working on. This is a rock called Tisdale. This would also be part of the Shoemaker Formation, but this one's different from the others that we've seen in that this was not bedrock exposed at the surface. This is a rock that was excavated from beneath the surface by that little 20, 25 meter diameter crater that we called Odyssey. And so this is a piece of ejecta that was tossed out onto the surface. You can see that it has a somewhat different texture. It's a very lumpy, very irregular surface. Lots of this is also a breccia. Lots of chunks in this breccia that are pieces of rock fused together in the energy of the impact. If we go to the next one, this is a microscopic imager picture, so this is about 3 centimeters across, and you can see the individual clasts or grains in this breccia, and they're typically a centimeter or so in size. What's really interesting about this rock, however, is the elemental chemistry. The next slide shows that. This is sort of a complicated plot, and what it does is it shows element by element the composition of this rock compared to a variety of different other rocks that we have seen. Okay, and I won't take you through the details here. I'll just point out one important thing. There's a ton of zinc in this rock. There's an enormous amount of zinc in this rock. The zinc concentration in this rock begins to approach the zinc concentration that you sometimes see in commercially mined zinc ores on Earth. This was a big surprise to us. Now, why would there be so much zinc? Well, when you find zinc ores on Earth, typically the zinc has been emplaced via hydrothermal processes. Hot water moves through the rock. It dissolves out different minerals. Those can then be reprecipitated, and zinc-containing minerals, particularly zinc sulfides, are among these, and they get concentrated along these lines of hydrothermal flow. And that's the way in which zinc deposits are formed that are mined commercially on Earth. It's easy to imagine that the heat, the energy of a big impact like formed Endeavour Crater could have set up these kinds of hydrothermal systems. So there's a nice coherent story that one can build around this zinc if, big if you believe that the zinc is found throughout this rock. Problem is we don't know that yet. If you go back one. One more. Look at the surface of this rock. It's incredibly rough and irregular. And our rock abrasion tool, which is still working, still works just great on Opportunity, was not designed to handle a surface this rough. This is an unratable rock. And so we have not yet been able to get inside of that rock and confirm that it's zinc-rich all the way down. This could conceivably be some kind of zinc-rich coating on the outside of it. I cannot rule that out on the basis of the data that we have. So I'm not ready to say hydrothermal system here because we haven't made that measurement. That's something we want to go after when springtime comes. Next one, next one, next one. Okay, now, to prove that we're geologists and not journalists, we totally buried the lead. Here comes the good stuff. When we first drove onto Cape York, coming right through here, we saw some very interesting, bright, linear features on the surface. We took note of them. They looked really interesting, really exciting. We were so eager to get up on the Shoemaker Ridge, we kind of blasted by them, figuring, okay, we'll go take a taste of Shoemaker Ridge, and then we'll go back down and see those things. Well, we had so much fun on Shoemaker Ridge that by the time we finished up here, it was getting to be time to head up to the north here and find a good place to spend the winter. So we decided, what we noticed was there's this kind of bench. You can see this topographic layer completely surrounding Cape York. And these bright linear features were so well exposed down here, we sort of rolled the dice and said, well, if there's so many of them here, let's just go on to the same place on the bench up here and see if we find them again. Next slide. We did. And the one that we examined carefully, we named Homestake. This is it. This is a pan-cam image of it. The Homestake feature is a very bright linear feature. It's about the width of your thumb, like a centimeter or so wide. It's a few tens of centimeters long. If you look at the next slide, you can see that it's topographically raised. This is a picture taken with a microscopic imager. It's about 5 or 6 centimeters across, and you can see this thing sits up above the stuff around it. Now, what we've done so far is we have made a measurement of the composition of this with our alpha particle X-ray spectrometer, which tells us about chemical elements, and this thing is chock full of calcium and sulfur. And calcium and sulfur in a ratio that points towards it being calcium sulfate. Now, as Ray mentioned, there are different kinds of calcium sulfate, one of which is gypsum. Gypsum is calcium sulfate that has some water in it, okay? 2 H2Os for every calcium sulfate unit. And when we look at this feature with our PanCam camera, which is capable of looking at a wide variety of different wavelengths across the visible and the infrared, what we find when we get out to the part of the spectrum where gypsum is different from the other calcium sulfates, that this guy looks like gypsum. There is a bend in the spectral feature in the spectrum that is consistent with what you see in gypsum. So we feel pretty confident that this is a material that is dominated by gypsum. I will not say that it's pure gypsum because we don't know that yet. This thing is only about 1 centimeter wide. It doesn't completely fill the field of view of our spectrometer. So what we're going to do come springtime is we're going to look for some more of these, some that are fatter, wider, will fill our spectrometer, some that we can grind off with the rat and we can really clean off. What we did was we crunched this thing with the wheels just to see what that would do to it. But this is basically a gypsum vein. Okay? And to me, this is the single most powerful piece of evidence for liquid water at Mars that has been discovered by the Opportunity rover. We have found sulfates before. Those sulfates were formed somewhere. We don't know where. They've been moved around by the wind. They've been mixed in with other materials. It's a big, jumbled up, fascinating mess. This stuff formed right here. There was a fracture in the rock. Water flowed through it. Gypsum was precipitated from the water. End of story. Okay, so there's no ambiguity about this, and this is what makes it so cool. Now, why gypsum and why here? The different sulfates that are present, there are iron sulfates, there are magnesium sulfates, there are calcium sulfates. Of those different sulfates, especially if you're talking about kind of moderate mid-range pH, calcium sulfate is the least soluble of the three. And what that means is that if you've got water with different sulfates percolating out of the ground, okay, and it's coming out of that ancient Noachian stuff, because remember, this is right next door to that very ancient stuff. Coming out of the ground, chock full of different sulfates, the first ones that are going to reach saturation, the first ones that are going to precipitate out, it's going to be the least soluble one, it's the gypsum. Okay? So what we think we are seeing here is remnants, if you will, of part of the plumbing system of the waters, the groundwaters that flowed through these ancient Noachian rocks and then created the sulfate sediments that we've been driving around on with Opportunity for 8 years. So as I said, this has been it's been an exciting time for the mission. We got a whole bunch of stuff to do through the winter with a very healthy and capable robot. We got a bunch of stuff to do once spring comes. We're going to finish up on Cape York and then head south across Botany Bay, and hopefully have some really exciting stuff to tell you about at the next AGU. So thank you.
Okay, let's go ahead with Q&A.
Christina Reed, Discovery News. With the zinc formation, is that the yellow, gold, cream color at the top? Is that all zinc? No.
No. The yellow, gold, cream color that you saw on the top, and that's an enhanced color. I should have mentioned that's sort of an enhanced color, false color image. That's just dust.
Oh.
That's just dust on the top of the rock. The top surface of all these horizontal top surfaces tend to get quite dusty, but looking at the cleanest surface we could find, that's where you see the high zinc concentrations.
And the purple, is that basalt, or is that?
Yeah, the bluish purplish stuff, it's fundamentally basaltic in character, but it has, as I said, this anomalously high zinc concentration at the surface. I wish I knew what was inside. We're going to try to find out in the spring.
Okay, and sorry, just the
Sure.
follow-up. You said this is with the gypsum, this is where water was. Any idea if there's still water?
There's certainly nothing to indicate water activity taking place beneath or at the surface at the Opportunity site now. No.
Hi, Eric Han with Nature. Can you, first of all, say when this water would have been flowing, and then if I could get you to speculate a little bit more about how and why or what was driving it?
Okay, sure.
And here at a crater rim, a topographic high maybe, that seems
Sure.
kind of strange.
Sure. As far as when is concerned, it's, I wish I could say with some precision. All we can do is sort of base it on the major stratigraphic units of Mars, but this would be after the Noachian, after the formation of that crater rim material. Probably, I would guess, reasonably early in the Hesperian period on Mars, which is the geologic epoch that follows the Noachian. Okay. So it cuts through these sediments. So obviously it has to be younger than the sediments through which it cuts. But if you want the age in billions of years, I can't give it to you because we just don't have that for anything on Mars, really. The other part of your question was, why here? There's actually some very nice work that's been done by Jeff Andrews Hanna of the Colorado School of Mines on exactly this subject. And what Jeff has done is he's used the topography of Mars and a pretty sophisticated model of groundwater flow to calculate basically from the topography and from the geopotential different locations on the Martian surface, where are places where water will be flowing downwards, where is you going to get horizontal flow, and where do you get primarily emergence of flow from the surface. And Meridiani Planum, which is Opportunity's landing site, is one of the strongest sites of groundwater emergence, according to this model, on the entire planet. It's what that simply means is that, yes, the rim of Endeavour Crater is a small local high, but if you look on a broader regional scale, there's a lot of stuff higher than this, and water is going to tend to percolate downward from that and then emerge in these lower-lying regions, and that's where you're going to find evaporation taking place and development of evaporite deposits like what we see at Meridiani.
Eric, there's at least a couple kilometers of hydrostatic head.
Yeah.
Because Meridiani is a tilted surface and the highlands are 2 kilometers higher.
Yeah. You got to look at the regional picture.
I have a couple of questions from webcasting. First is from Robert Zimmerman, 3 minutes. He was wondering how many Martian winters has Opportunity so far survived through, and could you expand on the difficulty of surviving through those winters?
Well, I haven't been on the mission since the very beginning. I believe this is the
We're going into our fifth.
winter. Okay, so we've survived 4 winters so far.
Yeah.
What was the second part of your question?
Could you expand on the difficulty of surviving this?
Well, the difficulty comes from the fact that these solar panels have been sitting out in the dust for 8 years, and we do get periodic cleaning events presumably from windy conditions on Mars. Those tend to occur later in the winter than we are right now, and so this is sort of the dustiest part of the year for the solar panels. So at this point, we have something like 45% or something like that of the 40% efficiency on the panels. So they're basically halfway covered up with dust. So we're kind of getting half of our power to begin with. As the sun gets lower and lower in the northern sky, we're getting less and less insulation on these panels, and so we just get less solar energy. It gets colder, so we need a little bit more heating, and so everything kind of comes together and makes this kind of a difficult time of the year for Opportunity.
The biggest threat to Opportunity's survival this winter is not dust on the solar arrays, and it is not the sun being low in the sky. It's the fact that it's a rover that was designed to last for 3 months that is now 8 years old.
But it's not a dire set of circumstances. In fact, what we're doing, as long as we're at 15 degrees tilt to the north or better, we can actually do some radio science experiments. We can continue to make APXS, or the chemical measurements, and do remote sensing. We'd even bump a little bit along outcrop and do a pretty extensive science campaign.
And then the second question from the webcast is from Michael Forster of Astronomy FM and Michigan Public Radio. He was wondering if either rover has ever imaged the Earth.
Yes. Yes, we did that with Spirit. There were times during Spirit's mission when we caught big wind gusts that really cleaned the vehicle off nicely, and we just had power to burn. And we would wake up during the night and take pictures from the Husband Hill Observatory, as we called it. And we took pictures of the Milky Way, we took pictures of the Magellanic Clouds, we took pictures of Phobos and Deimos, and we took a really lovely picture of Earth hanging in the sky. It's out there somewhere on the JPL website, but yes, it's been done.
Harvey Lyford, freelance. I would just like to get back to the naming question. My understanding is that these names are all unofficial, that they're not submitted to IAU.
Correct.
And probably the features are too small for them to be concerned with. Is that correct?
That's correct. The only feature name that we've given you today that's been submitted to and approved by the IAU is Endeavour for the crater.
Randy Shostak, reporter with EOS, newspaper of the American Geophysical Union. For Dr. Squyres, so can you say that there's no other explanation for what this stuff is?
This stuff being the gypsum?
The gypsum, yeah.
It's inconceivable to me that a fracture-filling vein of a water-soluble mineral that is a sulfate that is cutting through and overlain by other sulfates on Mars was not formed by precipitation from liquid water. I'll stake a lot on that.
The mineral has water in its lattice.
Yeah.
It has 2 waters in the unit cell.
You got another one, let me know. Because we're going to submit this to science real soon.
Hi, Irene Klotz with Reuters and Discovery News. Steve, you mentioned that this was the clearest evidence for water from Opportunity. Aside from the Mars Polar Lander's detection of the ice, is there any other more stronger evidence for water, past water on Mars? And could either you or Ray please put this into some context for how this might improve understanding of the Gale Crater site?
Okay, I'll take
Thanks.
the first part and let Ray handle the second part. Just going through the litany of water-related discoveries over at the Spirit site, the silica, the carbonate, I don't know if we got anything that stacks up against this one. I think this is just the single most bulletproof observation that I can think of that we've made with those 2 rovers this entire mission regarding liquid water. Not just, I mean, we've got a lot of things that have pointed at liquid water because of the mineralogy and so forth, but this is a combination of things. This is, in other instances, let's say the sediments, the sulfate-rich sediments that we've seen at Meridiani, yes, they have a chemistry that points very strongly to formation via evaporation, but they were deposited by wind blowing stuff around. Okay, here both the chemistry, the mineralogy, and the morphology of it just scream water. Okay, this is more solid than anything else that we've seen the whole mission. So I think this is the best one we've got.
We have seen at the Squyres site presence of opaline silica. So that's silicon dioxide, kind of amorphous with water stuck in the system. But we don't know the geologic context as well as this gypsum vein.
Yeah.
And
That's the difference.
The other part of your question is, so what, right? So we've been debating for going on 8 years now, exactly how these sulfate sandstones formed that we've been looking at with Opportunity. Beneath most places we've been, the section of sedimentary rock is hundreds of meters thick, and it's dominated by iron and magnesium sulfates, and some silica and some basalt. And we think they formed in these rising groundwater events. And they may have formed as mud. They've probably been moved by water, mainly by wind, mainly as sand dunes, and then rising groundwater would come up and cement them. And then they'd be eroded down for us to look at. But this is special because the combination of the chrism observation where Botany Bay seems to have gypsum, and then the veins with gypsum right in the bench very close to Botany Bay, stratigraphically and in terms of distance, suggests that something else is happening here. And it may be because we're at what's called a pinch out. So as we get up to the Nowakian crust, we're seeing the oldest rocks kind of sitting right on top of the Nowakian. And as those groundwaters would come up and out, the first thing to precipitate out, the least soluble phase would be gypsum. And the iron and the magnesium and a lot of the sulfate would be carried on downhill or elsewhere. And as the section would progress, you get more of these deposits moving from gypsum-dominated to iron and magnesium sulfate-dominated that we've seen. So it's another piece of the puzzle in terms of how what we call the aqueous geochemistry of Mars was working right at the end of the Nowakian and the early Hesperian.
Yeah, Rick Lovett, freelance. So I'm wondering how to put the two pieces that you've seen here together. You've got the sulfates, the gypsum, and you've got the possible zinc from a hydrothermal system. Mm-hmm. Can you explain, assuming it is not just a coating, how these relate?
They may not be related at all. They could differ in time by hundreds of millions of years. If the zinc really is the consequence of a hydrothermal system, best bet is that hydrothermal system was set up right when the impact took place. The crater forms, it deposits a huge amount of kinetic energy beneath the surface, which heats stuff up. The heat stirs up hydrothermal motions and produces hydrothermal alteration almost contemporaneous with the impact event itself. The formation of the Meridiani sediments could have happened hundreds of millions of years later with groundwaters percolating through fractures in the rocks and coming up to the surface. And so there may be no connection between those two whatsoever. Recognize that the bench material in which the veins are formed is contemporaneous with probably an early portion of the same sediments that we've been driving around on for 7.5 years. And then we crossed over the boundary into a very different, older Mars that's exemplified by the Shoemaker Formation. And so these are two quite very different stories. There may be no relation between them at all.
Jonathan Amos, BBC. Can you talk to habitability of these wet conditions vis-a-vis Meridiani and the sulfates that you saw there?
Sure.
Also, maybe the fumarole type silica deposits that Squyres saw.
Okay,
as
sure.
well, pH, that kind of thing. I mean,
Sure.
what sort of bug life would appreciate these conditions?
Yeah, this is one of the things that intrigues me the most about the gypsum, is that most of the evidence that we have seen so far with Spirit and Opportunity for aqueous conditions has been pretty acidic, low pH. If you look at the Meridiani sediments that we drove around on for so many years, they were chock full of jarosite. Jarosite is an iron sulfate, and it is one that is unstable above a pH of 5, and it typically forms on Earth at a pH of 3 or 2 or 1. So, run around saying water on Mars, water on Mars. What we really found there was evidence for sulfuric acid on Mars. The deposits that we've seen with the silica deposits that you mentioned that we've seen with Spirit, we got two different models for how that stuff might have formed. But you mentioned the fumarolic model. That is one of them. And it's one that makes a lot of sense. And the way the fumarolic model works is you have very low pH vapors that flow through these rocks and leach away almost everything else and leaves behind a very silica and titanium-rich residue, which is what we see. So, most of the evidence that we've seen with the rovers points towards a low pH. Now, the thing that is intriguing in many respects about the Noachian and about the rim of Endeavour is that, as Ray mentioned, there is evidence from orbit, from the CRISM data, that in some parts of the rim of Endeavour there are clay minerals, phyllosilicates, these smectites. And those tend to form under a much more neutral pH. An interesting thing about these gypsum veins is the gypsum is also consistent with, though does not require, a more neutral pH as well. And more neutral pH is going to be more favorable, we believe, in terms of habitability. So this is an emerging story, the story of the pH of the waters here at Meridiani. We're still working it. We will be searching very assiduously once springtime comes, both Cape York and further to the south, for evidence of clay minerals that may help to further advance our understanding of that story.
All right, I have several questions from the web. The first is from Ken Kramer, University Today. Please describe the plan for spring to look for phyllosilicates at Cape York and then the drive for Cape Tribulation, as well as the general plan for Cape York during the spring.
No, I won't. The reason for that is that we had a plan for what we were going to do at Cape York when we first arrived, and what we ended up doing was rather different from that. This is so new that our plans wind up being totally discovery-driven. We have a to-do list. We want to look for phyllosilicates. We want to learn more about the veins. We want to learn more about the zinc coating. We want to go to Botany Bay. We want to climb Cape Tribulation. We've got a lot of things that we want to do, but we will do them in the order and at the pace that makes sense as we discover things as we go. So we have a set of objectives. We do not have a detailed plan because what we're doing is discovery-driven. Sorry, Ken.
The second is a follow-up question from Robert Zimmerman with BehindBlack.com. He was asking why northern face photometry?
North-facing slopes because it's winter and the sun is low in the northern sky. That's where the sun is. So that's where we point.
Opportunities in the southern hemisphere.
Yeah, but more to the point, the sun's in the northern hemisphere right now.
And then the third from the web is from Alicia Chang with the Associated Press. Can scientists elaborate on Opportunity's winter campaign? Will it do any driving, or will it stay put and do science in place? Will it be active the entire time, or will there be some downtime? And when's the deadline for deciding where Opportunity will spend the winter?
Okay, sure. Yeah, I can go after that. The winter campaign, we expect the rover to be active and doing science all winter long. We are currently in a place where we have about 16 degrees of northward tilt, which is pretty much ideal. We will be making in situ measurements on bedrock. The bedrock that we're perched in front of right now, you notice when you look at these breccias, they're pretty heterogeneous. They got lumps and clumps of different types of stuff in them, and they may be different in composition. And so if we can really spend some time exploring this, we can look for a compositional heterogeneity in those breccias. As long as the rover tilt is that high, we can move around. We can't move far, but we can move from one place to another across an outcrop, and so we can conduct a very detailed campaign. We are in a good position right now to look into Endeavour Crater, where there are sand dunes and there are features that are produced by the wind moving different materials around from a fixed vantage point. We can watch those features as they change over a period of months. One of the things that we're most excited about is a geophysical campaign where we use Doppler tracking of the radio signal from the spacecraft to very precisely determine the spin parameters for Mars, which you can do if you don't move the rover too much. And that's related to things like the interior of Mars and whether the core is liquid or solid. So we'll work on that campaign this winter. So we have a lot of science that we have planned during the winter, and then of course as soon as conditions permit, and that depends on the sun moving in the sky, what happens in the way of wind gusts and so forth, as soon as conditions permit, we'll start exploring further afield. We're hoping to pretty much have the rover in place and sort of really kicking off the winter campaign no later than January next month.
But even after that, we can still bump.
Yeah.
We can still move a meter or two. And we're at a beautiful place called Saddleback, which is an outcrop that has a nice flat face, and we can slide along it during the winter.
I'm Charlie Pettit, Science News and Freelance. This is either Ray or Steve or Bruce. Two related questions. One is, you said the place looks almost like a new mission, a new place. And I understood that the localized features you saw are fascinating, the high zinc, the gypsum vein. But just looking at it as a geologist, how does it look structurally or compositionally different, except at the elemental level? And I'll take the answer to that question first.
All right. We're perched on the rim of a great big crater. Never done that before. Spirit spent its entire mission inside a great big crater, Gusev, which is actually even larger than Endeavour is. But we've never been to anything remotely like this before. It looks different structurally, it looks different compositionally, it looks different texturally, it looks different in every way. Now we can look at this and see some similarities to things that we've seen before. As I said, the geochemistry of some of these rocks is comparable to the geochemistry of some of the places that we've seen in the floor of Gusev Crater and on Husband Hill. If you look at the textures of these swavite breccias, they look at like stuff that you can see around ancient impacts on the Canadian Shield in North America. But the total picture doesn't look like anything we've ever seen on Mars before. That's what's fun about it.
Okay, and the other one is brief. Is there anything interesting about that bench around Cape York, or is that typical, or is it?
Go ahead.
Does it look like a beach or what?
No,
it wasn't a beach, but.
Well, we're still debating it. But the bench is interesting. It goes completely around Cape York. It goes around some of the other rim segments of Endeavour. It's probably an older deposit that kind of pinches out one of these groundwater rising events and forming these sulfate sandstones. And then it's been eroded to just form this bench-like geomorphic feature. But the veins are in the bench. You don't see the veins outside of the bench. You don't see the veins in the Noachian crust in Cape York. You don't see them in Botany Bay. As far as we can tell, for places we've been to on the bench, they're in the bench. So most likely what was happening is some rejuvenation, some groundwater upwelling event, and taking that calcium and sulfur from Botany Bay, those kinds of rocks, and then moving it up in veins on what's now the bench. The bench was probably more aerially extensive and has been eroded back. So it's telling us a story, and it's a boundary layer effect in contact with the Noachian, but we're still debating it. It probably wasn't a beach.
This is just a practical question. Given all the fuss and kerfuffle about budgets that we've had, how much does Opportunity cost now to run a year, and what sort of commitment have you had from the agency about your future? And are you guys going to get laser envy in August when the big guy arrives?
Well, to address the commitment from NASA headquarters, our commitment from NASA headquarters is renewed on a biannual basis. NASA has a process that they call a senior review process, in which all operating missions that are in their extended mission phase get up in front of a review board. Typically, all the Mars missions do it together in front of the same review board. And they present recent findings. They present their plans for future exploration. They describe the state of health of their spacecraft and instruments and so forth. And NASA then takes the advice of this review board and decides how to allocate funds. will in fact be coming up for another one of these senior reviews soon. I can't speak for how that senior review is going to go. I will say, however, that given the extraordinary health of this vehicle and the wonderful exploration opportunities that we have ahead of us with this vehicle, if we don't fare well in that review process, then shame on us. We haven't done a very good job of describing this story. So I feel pretty good about that. The current funding per year, Bruce, remind me,
it's about $12 million.
12, yeah, I think that's about right. $12 million a year. So to put that in context, it cost the taxpayers $800 million to get Spirit and Opportunity to Mars, and we're now doing this kind of science at $12 million a year. I feel pretty good about that.
Okay, Rick.
Yeah, I asked earlier about Rick Lovett about the linkage between the two, the zinc and the whatever. Could you put everything that we've got here, from the sediment or the early materials in which the crater was embedded, in order, tell the overall story for those of us who don't have all the geological strata memorized?
Okay, so I'll try to tell the basic story very quickly and simply. Long ago, an impact took place on Mars into material that was made of basalt. It made a great big crater, about 25 kilometers in diameter. The energy of that impact may have induced hydrothermal activity that produced the zinc enrichment that we see in places. Then, some period of time later, that may have been quite a long period of time, it could have been hundreds of millions of years, groundwater percolating through the surface came up to the surface. That groundwater contained rich concentrations of sulfate minerals, calcium sulfate, iron sulfate, magnesium sulfate. Some of those minerals were precipitated out in fractures that lay very close to the crater rim, and it was the calcium sulfate, the gypsum, that precipitated first. Then that stuff came up to the surface, water evaporated away, precipitated out all the other sulfates, and those blew around and produced the deposits that we've been driving around on for the 7.5 years before we got to the rim of the crater.
And Endeavour is one of many, many craters. You can see to the south of where we're located, a couple hundred kilometers, that ancient Nowakian terrain is exposed, and it's dissected by channel systems. And as we come to the north from that exposure, those materials are buried by the sedimentary rocks we've drove over for 7.5 years. So there was formation of those impact craters, dissection of the terrain probably by snowfall, rainfall, runoff, and then moving to this kind of groundwater upwelling event to produce the sulfate sands.
Thanks very much to our panel, and for anyone in the audience who wanted a link to the picture of Earth by Spirit.
Okay. Our next press conference is going to start at 4. It is a megaquake brewing in the high Himalaya, and I have to ask that if you want to interview the scientists, if we could please go out into the hallway to do it, I'd appreciate it, because we're going to have another press conference starting very quickly.